Well, welcome to the M-OSRP Executive Summary of February 20th, 2015. M-OSRP is about solving the right problem. Solving the right problem for us means identify and solve problems whose solution would have the biggest positive impact on the ability to effectively explore for and produce hydrocarbon. How our group in its history has provided value towards that mission, and what it's doing currently and what its plans are in terms of identifying and problems that are serious and significant, and how this group has, is, and will continue to deliver added value to our sponsors. So for some background detail, this set of links can provide detail that we might refer to in this talk, but will not have time to describe. So seismic E&P challenges. So how do you know there are challenges? Andy Hawthorne, great scientist at Schlumberger, has slides which he uses frequently that show that the Department of the Interior of the United States, the Mineral Management Service, has statistics that show in the deep water Gulf of Mexico, the success rate of exploration drilling is 1 in 10, and it hasn't changed in 10 years. That's the other part. So that statement says that there are some issues. If 1 in 10 is a successful drill in terms of reaching the target, and it's not what we expected to be at the target, 1 in 4 has to withdraw because there's a shallow hazard that was unforeseen in the seismic data. So there are no shortage of challenges. And one aspect of what we'll be discussing today is what I call the seismic exploration processing disconnect. You have this statement that Andy Hawthorne shows and that the Department of the Interior publishes, and then you have what we hear at SEG and EAG conventions, and you read it in publications, where you can't see a single problem. Everything is just one success after another. That disconnect is exactly what this group is about. So why are there challenges? Every method, scientific method, has is a model. It makes assumptions. When those assumptions are satisfied, things or methods are effective. And when they're not satisfied, the method will have difficulty, and that is one of the causes for dry hole drilling and suboptimal development drilling. There are different types of assumptions. Your methods have certain types of data that need to be acquired. Methods have required compute power in order to have reasonable turnaround time. And last but not least, methods themselves have innate algorithmic assumptions and requirements that are part of what you see when you derive the algorithm, that you cannot attribute to lack of data or lack of compute power, the assumptions within the algorithm itself. In this group, we feel there are two ways to address challenges. One way is to remove the assumption violation by satisfying the assumption. The other, if you can't find a way to satisfy the assumption, then seek a method that doesn't make that assumption. This group adopts one or the other of these approaches for different challenges. So M-OSRP takes ownership and responsibility for the entire processing chain. Everything that happens to seismic events from the moment it's recorded, every single type of event, and through every objective that we have in mind for processing seismic data. Among innate algorithm assumptions are many processing methods require subsurface information. In complex and ill-defined areas, that requirement can be difficult or impossible to satisfy. The inability to satisfy that requirement can lead to algorithmic failure and dry hole drilling. So it turns out that we see two ways of dealing with challenges, assumption violations. One is satisfy the assumption, the other is avoid the assumption by having an algorithm that doesn't require that assumption. There turns out to be an extremely popular and widely used third method for dealing with challenges, and that is ignore the assumption, ignore the problem, okay? Act as though the problem doesn't exist. That is a very common attitude to the most difficult challenges that we face in seismic exploration. And to not mention that in this talk is not to have a frank and forthright discussion with those who sponsor us and sponsor other activity. To give you two examples, David McKidd, who was at Encana, and Bill Goodway, who was at Encana and who is now at Apache, said in their long experience with onshore data in Canada, the common statement was, there are no internal multiples. There just are none. Just ignore them, act as though they're not there, and then go forward. That is ignoring a problem of tremendous significance, and what David McKidd calls ignoring the elephant in the room. That is not a small issue. You just say, there's no problem, okay? Just, we solved it, just ignore it. Another similar type of problem was mentioned by John Etchen in this year's Recent Advances Road Ahead at the Denver SEG meeting, where he stated, in a very rare and courageous statement of high integrity, professional and personal integrity, that the biggest challenge today in doing seismic imaging is the inability under complex circumstances to find an adequate velocity. That statement, I had never heard anyone give a talk and say that statement before. And he said that tomography methods, common image gather flatness, FWI, all good, all have made some progress, but all together, taken separately and all in combination, do not represent a candidate, a realistic candidate fulfilling the gap between the challenge that we face in velocity analysis and the current ability. That's a very serious statement. It's not only serious because it's a problem that's ignored, but many people make assumptions that that problem doesn't exist, that velocity analysis is a solved problem, or it needs minor tweaking, that it isn't a major difference between the nature of the problem and the nature of our ability to address it. That big gap is part of what this group is about, for both what David McKidd and Bill Goodway are talking about and what John Etchen is talking about, that kind of clear, not avoiding the most complicated and difficult problems, not working on problems that assume the most difficult problems have been solved. So you have all kinds of methods of migration that are doing anisotropic migration, reverse time migration, more and more anisotropic parameters, ignoring the fact that for a heterogeneous acoustic medium with a rapidly varying velocity, we can't find a velocity. That reality is important for us to digest, and it's not the kind of statement that will make John Etchen popular, and it certainly won't make us popular. We're not looking to be popular. We're not running a popularity contest or an election. What we're looking for is to stay focused on the problems that will really make a difference, and they're hard problems, and that's why they take a long time. Some of the methods that we develop are unconventional and cause people discomfort. We recognize that new thinking will have that as a concomitant activity. The bottom line is, because we recognize and identify problems that others often will ignore, and therefore just mentioning that certain problems are problems already causes us an issue. That lets you know how deeply grateful and appreciative we are for the support we receive. We understand that what we often communicate is difficult for researchers to accept, and we depend on researchers in industry for our support. That's the trick. Yes, we've learned in our history to depend on people in operating units for what the problems are. They will tell you what the obstacles are and when methods are working and when they're not working. And that is an important place for where M-OSRP starts and where M-OSRP acts. Okay, so we're looking for these kinds of problems that can often be ignored. In other words, if you ignore the fact that velocity in complex regions is not achievable, just ignore it. Then we'll judge progress on imaging as though velocity was known. So we'll have all kinds of improvements in the imaging world that make an assumption that's not realistic. And then we have modeling methods, large-scale, industry-wide modeling methods that match the assumptions of the imaging algorithm. So one issue is the velocity itself is difficult to determine. And another issue, separate and important, is imaging through it. Even if you had a perfectly known complicated velocity, just getting a wave predicted beneath it is non-trivial. So what happens often? We run big, large-scale modeling efforts where the velocity that's used in that modeling is smooth. So it makes those imaging methods look good. That's part of the disconnect. That is part and parcel of the disconnect. So there's another part. It's not only, John Etchen was saying, it is the problem, the inability to find an adequate velocity. It is a big, serious, major problem. But as John and we understand, it isn't the only problem. You can have, as a group from Total published a paper in EAGE a year or so ago, showing difficulty in imaging layered 1D Earth in the North Sea. Bertrand Dupuy and his colleagues. It was a layer cake problem. It's not a velocity problem. The problem was the internal multiples there was so horrific that every primary had a multiple sitting on it. And the inability to remove those multiples without damaging primaries was the obstacle. So there are times when multiples were and remain an issue. And that's part of what we're after as well. Okay, so this is a tree, we call it, which what happens is that dot on the top represents seismic events that have been recorded, let's say, in the ocean, when you're towed streamer. And then what happens in seismic processing is there is a set of separation of events, cataloging of events. That's found to be useful, and there's first a separation into what we call the reference wave and the scattered wave here, reference wave and scattered wave. And then the scattered wave, meaning the reflection data, is deghosted. The ghosts are separated from the non-ghosts. Ghosts mean events. Deghosted data are events that started their history moving down from the source, and when they're recorded are moving up to the receiver. So there's a separation, the ghost, no ghost. Then all reflection data that have no ghosts are separated into free surface multiples and primaries and internal multiples. Then primaries and internal multiples are further separated into primaries and internal multiples. And then first by reducing, and then you'll see eliminating internal multiples. Then with the primaries, this is the signal bearing part of seismic data. many things can happen. There's a set of procedures that allows you to do depth imaging without a velocity model. You can do direct inversion for medium properties, either in a static sense, finding changes, and we'll discuss that a bit later on, changes in material properties. You can do Q compensation without Q. And then there's a more recent sort of an anomalous project here, which is a new and more effective way to do RTM for both amplitude analysis and for imaging beneath rapid variations compared to what's done today in industry. So this tree is, you can see, is a set of separations. The events get separated, further separated, and then things happen at some point. These separation methods, you see some have green dots. What that means is the green dots, Green's theorem allows that separation, and the yellow dots are another method called the inverse scattering series that allows this separation from a different point of view. All the dots here act. All the dots act. All of this, except this one, act without velocity information, whether it's Green's theorem or for separation activity. So since Green's theorem is one of the tools, Green's theorem is a fundamental building block for mathematical physics. Started 1826, George Green will say a word about it because it is involved in several of these cataloging activities that, that this group is involved in. Every single bullet on this tree, M-OSRP has had an impact on that makes a difference in industry. Every single bullet here, without exception, and in some cases unique. And so we'll improve deghosting, improved wave separation of scattered and reference. We'll make clear what we mean by improved, as this set of presentations that you're going to hear today is going to take you through this tree and give you examples of current and ongoing progress on every single bullet on the tree. That's a way of describing what's going to happen here today. So Green's theorem tutorial. As I said, it's a way to, one of the things that Green's theorem does is it gives you a way to separate wave fields, and there's a lot of separation of events going on in seismic processing. So just to illustrate that activity, here's a wave equation for a pressure wave in an acoustic medium with a velocity C of R and some wavelet A of omega and some localized source. Just as way of illustration of how Green's theorem works. If you write this velocity configuration, C of R, in terms of a reference velocity and this function alpha, then you can rewrite equation 1 in this form, and then you can take both terms on the right-hand side, this term and that term, and call them a source term rho. One way to solve equation 4 is in terms of a Green's function, which instead of having rho has a Dirac delta function. You can get the causal solution for that function P, let's say a pressure field for any point R in space, in terms of a superposition of the causal Green's function solution to phi and the weights that occur in P's differential equation. There's another form of describing a relationship for predicting waves and wave separation. It comes from Green's theorem, involves in this context a relationship involving G0, the Green's function, and P. Ends up with this formula, which is a prediction of the pressure field in a volume in terms of the integral of the sources in the volume and the surface integral, a closed surface integral. This equation 8 is going to play a big role today for both wave prediction and wave separation. Wave separation comes by choosing the G0 in 8 to be the causal G0, and then you get a comparison between 9 and this equation, which we relabeled it as 10, the all space one, and get this famous formula. It says that the contribution to the field inside a volume due to sources outside the volume can be given as a surface integral. The contribution due to sources outside to the field inside can be given as a surface integral. Before we run off, there will be a moment in today's presentation where P as a predictor of the wave inside a volume will be called on, because in wave equation migration there is the need to predict what a receiver and source will experiment inside a volume would measure in terms of what measurements on a surface would provide. This rho, if your knowledge of what's inside that volume is perfect, there is no rho. Rho gives you a difference between the reference velocity and the actual velocity. If you assume your reference velocity is actual, there's no term here for that rho, for the scattered wave. So this will come up when we talk about a new method for RTM. Right now it's being described in terms of its wave separation properties. It's also a wave prediction machinery. So we said, gives you the contribution, the surface integral, gives you the contribution to sources outside to the field inside. What does that mean, source contribution due to the sources? It means you have a reference medium, and then the world is broken up into a reference medium and what you have to add to the reference medium to make reality. So if, for example, you start off with, in the marine case, a reference medium which is air, a half space of air, a half space of water, then what you need to add to this picture to make reality is an air gun in the water, a source of the wave, and the earth. So there are two sources here. 1, 2, for that reference medium, for that discontinuous reference medium. If you take a closed volume like this and evaluate it for a point inside that volume that's integral, you will get the contribution that the air gun produces to the total field here in that reference medium. In that reference medium. And if you similarly close this way on top and you evaluate that integral inside the volume, you'll get the contribution that the earth produces in the reference medium of air and water. Yes. So that's a way of predicting these, what we call the scattered wave and the reference wave in terms of Green's theorem, a wave field separation concept that this group in its history has pioneered for marine application, and you'll see Jingwu talk about for onshore application. So this is showing you that what I just said, that you can separate the reference wave and the scattered wave. And one way, and if you assume the reference wave is an isotropic source, it's a way to get the wavelet in terms of the field and the normal derivative on the cable. Another application, important application, is not to separate the scattered and reference wave, but take, for example, the total wave or the scattered wave and deghost it. Deghost it means up-down separation. From a total field at a point, what part of that field is moving up at a given receiver, let's say. So if you pick a homogeneous world of water, different than we had before. Here the whole reference medium is homogeneous, all space water. Then you have three sources, air, air guns, and earth. And each is just producing an explosion, rho times G0 plus moving away. So if you compute, for example, the take an integral like that, like what I just drew, let's say you have a cable and you close it, then you evaluate at a point like this, you get a contribution due to roll earth in that reference medium, which is an up wave. If this evaluation point is below the air gun, then the air gun in that G0 plus is a down wave. The air is down, so that the contribution to the total field due to the earth is the only up component, and hence that's the deghosted receiver data. Okay. This is equation saying that. So if you put in here G0 whole space with the same formula that you, instead of G0D plus G0FS, you can do deghosting, just as you originally had an earlier example where you separate the reference wave from the scattered wave. So these are Green's theorem applications for wave separation of the scattered wave and the reference wave, and then further to deghost data. Okay, you'll notice those previous formulas required the field in the normal derivative. These days, that's not much of an obstacle in the marine case, but onshore, if you have buried sources and receivers, and we'll discuss that later, over-under receivers is not common. Even on land, over-under receivers on land is not common. What are you going to do? This apparatus here, without going into detail, it's in our literature, allows you, if you have knowledge of the source signature, either its wavelet or the wavelet and radiation pattern, then that knowledge can substitute for the normal derivative. So that's something to keep in mind in applications. Okay, so the next presentation, since we just described Green's theorem for as early on in that tree, Dr. Germain now is going to show application to of those algorithms to synthetic and field data.
Thank you, Dr. Wegline. The first application I want to discuss is a synthetic data set that you are probably very familiar with, which is seam phase 1. I had the opportunity to apply Green's theorem to seam phase 1 data thanks to PGS. And just a reminder, seam phase 1 is a 3D acoustic model of deep water Gulf of Mexico. It has sources at depth 15 meters. It has over and under cables at depths 15 and 17 meters. And this shows you applying Green's theorem to a typical shot pattern in seam data. On the left, we have the shot pattern, and we can see, indicated by the red arrow, the water bottom primary and its receiver ghost. And on the right, after applying Green's theorem, you can see that the receiver ghost has been removed. And in fact, if you look closely, you can see that there's a lot of distortion of the primary by the proximity of the receiver ghost, and yet Green's theorem effectively removes the receiver ghost, leaving a primary. The next data set that I applied Green's theorem to, again thanks to PGS, was some of their field data from the deep water Gulf of Mexico. And the field data was acquired using sources at 9 meters and a dual sensor cable being towed at 25 meters. And applying Green's theorem, we can see that we have removed the ghost because we're doing a frequency plot where frequency is on the horizontal axis, amplitude is on the vertical axis. And if we look at the blue line is the acquired data. And as you all know, you have destructive interference between upgoing and downgoing waves in the water. That destructive interference causes what are called ghost notches, where you're losing data at multiples of 30 hertz in this case. Applying Green's theorem nicely removes the ghost notches, which is shown by the red line, and hence we've recovered data. And this is called broadband in much of the literature. I also had the opportunity to apply Green's theorem to ExxonMobil data. This was deep water North Atlantic data, where they had over and under sources at 13.5 meters and 18.5 meters, and over and under cables at 20 meters and 30 meters. The results, I had permission to show the results in my thesis, not anywhere else, so I give you the reference here. My thesis, figure 216, shows how effectively Green's theorem removed receiver goes from this deep water field data. We're going to shift gears now. A previous student, Jingfang Zhang, in his thesis, showed how effectively Green's theorem can be used to pre-process data for the inverse scattering series that Dr. Wedline mentioned a few minutes ago. This is the model that Jingfang used for his data. You can see the source at depth 2 meters and a single towed cable at depth 6 meters. And because it was synthetic data, he knew the source signature. Now, what this plot shows is he used Green's theorem to deghost, and then he applied the deghosted data to the inverse scattering series free surface multiple removal subseries, and he applied only the first term of that free surface multiple subseries. And what it did, as you can see by comparing the red line, which is the data before receiver deghost, before removing the free surface multiples, with the blue line, which is after applying the free surface multiple removal algorithm. The primary is untouched. The first order free surface multiple is completely removed. And then the second order and third order free surface multiples are pre-processed by the first term in anticipation of their being removed by second and third and higher terms. This just says what I said on the previous slide. And I will turn it back to Dr. Wedline.
So before we move beyond Green's theorem in terms of wave separation application, as Dr. May mentioned, we need to say that when we say M-OSRP, I mean by that M-OSRP and those individuals that I was fortunate enough, colleagues and students, to work with prior to arrival here that have influenced what we know, what we're expert at. And in this particular area, I need to mention Bruce Seacrest, Lasse Admundsen, R. Olsen, Hing Tan Chell, Jingfang Zhang, and Dr. Mayen, among those who've made significant contributions to that these type of wave separation methods. So what is it that M-OSRP has delivered in terms of wave separation methods that stands alone compared to what's available in industry? It stands alone in the fact that industry typical deghosting is basically up-down separation on a horizontal layer, a horizontal measurement surface. And if you take the methods, as Jing Wu will show in our onshore applications, and Fourier transform those integrals, you get products. And this reduces, under that special case, these wave separation methods for deghosting to what's called PVZ. That is industry standard, okay? That you will find in many service companies. What has been contributed here that differs is that is a special case of that Green's theorem integral when you have a curved corrugated ocean bottom or onshore and you're doing deghosting. And if you use PVZ, which is often done, that's a serious error, that difference in topography. If you know that topography, you do that surface integral on that topography and you evaluate the deghosted data at a point above that topography, and you have made no assumption about it being horizontal, and that is not PVZ summation. Yes, that's a differentiator. So, as Dr. Mayen said, there's a lot of interest in deghosting called broadband for other purposes, and we're happy about all those other purposes. That tree says, in order to do the steps further down in the tree, every inverse scattering series, for example, application requires first separating the reference wave from the scattered wave and then deghosting the scattered wave. Every application. If you don't do those two effectively, everything subsequent will suffer. So they're essential, and that's part of what Dr. Mayen just showed. In Jingfang Zhang's result, he had source and receiver deghosted data, then Carvalho free surface multiple elimination eliminated that first order multiple with one term in the series. You need to say right here and now, if you're using SRME from Delft, as many companies do, as almost like Kleenex means tissue, you are not going to predict the amplitude of a free surface multiple at all offset, period. Okay? And so if you want that kind of effectiveness that you just saw of removing an internal multiple, a free surface multiple, then you need to use the inverse scattering series free surface multiple that was pioneered, developed by Paolo Carvalho, a former student. Okay, so that tree had all these green dots for separation methods that have to do with Green's theorem, and it had yellow dots that have to do with inverse scattering series separation and processing. So the inverse scattering series is a different set of methods. Briefly, it's potential, it's perturbation theory, and what it means is you have a source, you have a medium, a wave goes off, and there's a wave in the medium and outside the medium. Scattering theory represents the relationship between a change in that medium and the corresponding change in the wave. So if you consider L0, G0 to be the original medium, this being the properties of the original, this is some kind of idealized wave field, and L being a change in properties from L0, producing a field G with the same source delta. If you define V as a perturbation operator between the differential operators that govern propagation in the original medium and in the new medium, perturbed from the original. V is a difference in differential operators. Each operator contains properties of its respective medium. V is therefore the difference in properties. There is an equation, an identity, that relates the wave in the new medium, the wave in the original medium, the wave in the original medium, and the wave in the new medium, and V, which is a difference between properties in the original and the new medium. This is a relationship. This is not a solution for G. If you iterate this and substitute the first approximation for G being G0, and then repeat that and continue to repeat that, you get an iteration like this, a series, very old series, called the Born series by physicists, the Neumann series by mathematicians. This is not new. This is at least in the 1920s was known. So this forward series is a modeling machine. It's a modeling machine that one way to interpret it is, in normal modeling, you have L and you produce G. This is perturbation theory, so you don't directly produce G in terms of L, you produce G in terms of L's pieces, L0 and V. L0 enters as G0, and V enters as itself. And this series then says the difference in the wave field between the difference in the wave anywhere in the medium, outside the medium, the difference in the wave field is nonlinear to the change in properties. Linear, quadratic in V. V represents the difference in properties. So that is a very important statement. It says any change you make to a medium, it doesn't matter how big, how small, what nature of the change is, then the change in the wave field is nonlinear to that change. And so the important point to realize here is this is a geometric series. If you think of this, a generalized geometric series, AR squared. So if you look at it that way, this structure, where did that structure come from? This structure came from that equation. So to recognize this, you needed to have scattering theory equation. Yes. Once you have that, that is a modeling machine. So you see, this is the portion of G minus G0 that's linear in V, the portion quadratic in V, and so on. The inverse problem is from measurements of G minus G0 outside the region to determine the median. If we assume we know the reference medium, L0, then the task is to determine V. Just as the scattered wave, G minus G0, is a power series in V, or VG0, V itself can be expressed as a series, linear, quadratic, cubic, in the data. The data means G minus G0 measured. When you take equation 3 and substitute it into equation 2, you get this set of equations for every one of those terms, V1, V2, and so on. So this set of equations has a radical and upsetting to some people message, but it's unambiguous and unequivocal what it says. It says that to solve for V1, the first term here, you have measurements and you have G0, a Green's function in the reference medium. If you, the second equation to solve for V2 involves V1, which is essentially the data, multiplied by the data, and the inverse, if you were looking for V2, involves the same inverse operation as for V1. Every single term here, this, let's just say you were in water, and G0 was propagation in water. Then to get V1, you would invert two G0s, which are water speed propagation, which you can do analytically through Fourier migration. In other words, the solution for V1 in terms of your data is an analytic, not a numerical operation. Similarly, V2 is analytic, has the same form. So this, this scheme here says you can solve for every term in the inverse scattering series directly in terms of your data and G0. Directly means, what does it mean directly? It means there's no search, there's no optimization, there's no cost function. This is an analytic inverse. The only thing you have here is data multiplied by data. So this is very different than iterative linear. Where did iterative linear, FWY, and all that separate from this? Where it separates is it doesn't start with the scattering equation. It starts with an assumption that the forward problem is a Taylor series. That this is a Taylor series. It is a Taylor series. It's a very special, very reduced, very specific type of Taylor series called a geometric series. And a geometric series has an inverse series. A Taylor series does not. That's why they do a linear update. Okay? Now, linear update is fundamentally different than this, and it is leads to numerical inverses, because as soon as you take V1 and add it to the reference, V1 cares about your data. So your new Green's function is going to care about the data. The inverse is going to be numerical. You're in error space. You're in mathematics. You're in choices of weights and choices of which generalized inverse, and you've lost the physics. This is, don't touch it. Okay? In addition, what we do here is, this says that the whole inverse machine for V is achievable order by order in the data, order by order in the data. You get a linear quadratic. Directly in terms of water speed, and your data. If you imagine that you have an inverse machine like this, and in comes the data and out comes the Earth, then you can imagine that there are tasks achieved within that machine, like free surface multiple removal, internal multiple removal, depth imaging, nonlinear AVO, Q compensation. All those tasks have to be in that machine. They are what we call isolated task subseries for those different tasks. Every one of them, every term, every piece of every term of this series only cares about your data and water. So if you have an isolated task subseries for internal multiple attenuation or elimination or depth imaging, if it comes from that series, it cares about, every term cares about data and water speed only. That's the message. Okay, so if the task that you're after is like multiple removal, free surface or internal multiple removal, when you look at this, you don't even do an inverse step. This is data. Data. You don't touch G0. There is no inverse step, as you'll see, when you do multiple suppression of elimination or attenuate of internal multiples, or eliminate, because you never even invert through a water speed inverse. You only do that if you're into model space. If you actually want to get depth image, let's say, or changes in Earth properties. As long as it's a process that involves data in and data out, there is no inverse step. It stays like this, and you just have multiplies of the data outputting forms that you'll see that require, there's no inverse step, not even an analytic inverse step. No inverse step. Okay? For anything that involves data in, data out. So this is a very different scheme than is conventional in seismic exploration. It's very different than inversion in every field. It is direct and requires no subsurface information. What is the benefit of direct? It's not indirect. Indirect has some kind of replacement for a direct solution by looking for a cost function. Even if you had a cost function or cost functions which were necessary and sufficient, you would still be searching, and you don't know when you're done. You don't know when you found that global minimum. So that's, first of all, and more often than not, your indirect cost functions are necessary but not sufficient, like common image gather flatness. Okay? That's a necessary condition but not sufficient that you have the right velocity. So there's two things. This is not, there's no search here. This is direct, order by order solution in your data for whatever your task is about. And in addition, separate from that, it requires no subsurface information. Okay, we're going to say a word about free surface multiples to give an example of the inverse scattering series in action. Here's a very simple cartoon. Consider a world which is layered. There's a unit pulse going down, and there's a single frequency component of a wave moving up. There's no free surface there. So that R of t corresponding to R of omega would be a trace consisting of primaries and internal multiples. Primaries and internal multiples are R of t, and R of omega is its Fourier transform. Now consider the same Earth, but now put a free surface here. And now look at the data produced by a same unit pulse down and the upgoing component of what that receiver in the water measures. This picture right here assumes deghosting. That the events that R sub f of omega consist of are due to a wave straight down. not up, down, and straight to the receiver, not up to the free surface and down. So this is a deghosted experiment to begin with. So assuming deghosted, what we're going to do is we're going to derive this from that. We're going to make this from that. The objective is from this to make that. We want data that has primaries, internal multiples, and free surface multiples deghosted to become primaries and internal multiples. Then you will have removed free surface multiples if you can go that way. Now how we're going to go that way is go that way, and then just turn the equation inside out. So here's this unit pulse going down from that source, hits the Earth, out comes R of omega. R of omega exits the Earth, a train of primaries and internal multiples, and that train heads north through the water column, hits the free surface, picks up a -1 reflection coefficient, and heads south through the water column back into the Earth. That whole train of primaries and internal multiples, here, this train of primaries and internal multiples heading south is effectively a wavelet. If one enters the Earth, produces R of omega, then when this enters the Earth, it produces this wavelet times the impulse response, or that. So then this hits the free surface, picks up another minus, plus comes down and continues this way. If you pick up all the up waves here, up, 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 why? Because we're assuming deghosted. In other words, this receiver here is finding a wave moving up and then down past it. The down past that receiver we're ignoring. That's what deghosting means. Yes? So if you take all those up waves, you get R minus R squared and so on, sums to this. This gives you deghosted primaries, internal multiples, and free surface multiples as a infinite series of data with primaries and internal multiples only. The only assumption here, two assumptions, very important. One is the convolutional model, that if 1 produces R, then minus R produces minus R times R, yes? And that -1 is what it hit, and that deghosted data is here, yes? Given those three, and only those three, you got this equation. You can take this equation and invert this, solve for R in terms of RF. That's what you want. This is data consisting of primaries and internal multiples in terms of data with primaries, internal multiples, and free surface multiples. You can then expand this as a geometric series. This is the free surface multiple elimination series that Carvalho pioneered, and is a very elementary example of what the inverse scattering series will produce. This is your data, deghosted primaries, free surface multiples, and internal multiples. That data multiplies itself, one frequency at a time. And the operation of this time, this plus this, does two things. Every multiple that hits the free surface once is eliminated. And in addition, every higher order free surface multiple, higher order means has hit the free surface more than once. Every higher order is altered such that when this plus this plus this occurs, second order is eliminated, first and second. So there's a constant cooperation going on here, not only between events multiplying each other, but the terms in the series cooperate towards their goal. Any term by itself does not do everything that's only good, but everything that it does that appears to be good and bad, from the series point of view, the bad is purposeful and necessary. If that negative alteration of higher order did not occur when this added to this wouldn't eliminate second order. So that's an amazing characteristic. This is something that we didn't derive. We took that set of equations, V1, V2, and we mine it. The brain is in that one slide. All we're doing is mining the potential. We don't derive the internal multiple. We don't derive the internal multiple elimination. We look for where it resides. We're not, okay, we don't dream up these things. We look at that one slide, where is that activity inside that series, and we extract it. It's there already. There are terms there that we have not yet mined that are there already, yes, waiting for us to extract them. So, another item. This this free surface multiple elimination method works at one frequency at a time. 5 hertz, if you have 5 hertz in your data. If you don't have 5 hertz in your data, then you don't have 5 hertz in the free surface multiple, and you don't eliminate anything. There's no problem. 10 hertz doesn't care about 5 hertz. One frequency at a time this works. And it's only data. You see any inverse step? You see anything being inverted? Take the data, multiply it by itself 3 times, and add them. There's no G0 inverted, because it's data in, data out, to that point I made earlier. More importantly is, where was the water bottom? It doesn't matter. Was this earth acoustic, elastic, anelastic? It could be absorptive. You don't care. This formula doesn't change. The free surface multiple elimination method and the internal multiple attenuation method that you'll see in a second are not only do they not care about subsurface information, they don't care what earth model type you have. You tell me, I got this latest, greatest anisotropic view of the world, and you say, well, how are you going to change your internal multiple algorithm or your free surface algorithm? Not one line of code changes. That's incredible. Not only doesn't care about earth properties, does not care about what earth model you have at that moment, whatever the current flavor is. Okay? So what this shows, this is a work of Chalma showing how alteration of higher order then gets fixed later. Let me show you a different example. This is an amazing example. This is an example where we cooked up a primary, a free surface multiple, and another primary. And we cooked it up so that these two events, this first order free surface multiple and this deeper primary, have exactly the same travel time and opposite amplitude. So when you add them up, you only get this primary. Yes? You take this, you take that data and put it into the free surface algorithm, and you will recover the hidden primary, R2 prime. In other words, on your data you'll see one event. The algorithm knows that if you have a water top, it must have free surface multiples. It starts computing them from your first primary and then subtracts it, and that hidden second primary comes out. This ability to recover a primary that's proximal and interfering with a free surface multiple, if that's your issue, you need to look at the inverse scattering series free surface multiple to have fidelity at all offset. Before you do that, you need to remove the reference wave, and you need to do source and receiver deghosting, and then what Cavallo produced, that free surface ISS algorithm, will surgically remove that multiple, proximal to a primary or not. That will not happen from SRME. I'll repeat that. What I just said, if you do SRME on that interfering primary and multiple, you will not recover that primary. Okay? You'll get a damaged primary. It will alter it because of the problems with SRME at different offset. And you definitely don't want to do adaptive subtraction when you have an interfering primary and multiple. We're pointing out things to understand that the value that this group in its history has provided and that we can benefit from. This is the grown-up form of the free surface algorithm by Cavallo. This factor Q is what's missing in SRME. That's a frequency and angle dependent factor that will affect the fidelity of the prediction. It's that simple. This is the internal multiple attenuator. Data, data, data. There's no inverse step. It just data multiplies data, just like in Cavallo. Data times data produces another data. There's no inverse. So we're going to show you a recent example, very impressive example, carried out at Petrobras by a student here, Andre Ferreira, with a group at Petrobras and with assist from Paolo Terengi, who is here. This is stack before free surface multiple, stack after, and when they say free surface multiple, they mean Cavallo free surface multiple in Brazil. Okay? Then internal multiple results. Focusing on that panel on the right. After ISS attenuation, before. There's a salt layering here. Nobody knows here what the salt layering is. We don't need to know the region of the generators. We don't need to know. There's nothing known. Just in comes the data, out comes the result. So there's a word called data-driven. Data-driven. It's abused. Data-driven. Seismic processing is data-driven. Data comes in and we do things like find the velocity. Does that make velocity analysis data-driven? So when we're talking about here, we're very specific. The data comes in and there's no subsurface information found. Okay? That's what we mean. No information needed, determined, or estimated. Just the process carries on in terms of data and water speed. The conclusion in Petrobras was no other tested method was able to attenuate the sequence of internal multiples before the salt layer. Now Chung Fu is going to talk about his experience on land.
So thanks for the opportunity to give this short presentation. And from Dr. Begler's introduction, we know that ISS internal multiple attenuation algorithm needs some prerequisites to be effective. And some of my colleagues will tell you how to better satisfy those prerequisites. And other of my colleagues will tell you how to make the algorithm itself stronger. But before we get there, let's look at the standalone capability of ISS internal multiple attenuation algorithm on land data without any further effort. So in this short presentation, I will show you three tests, both of synthetic and field data. All results are done by my colleagues in Saudi Aramco and myself when I worked for Saudi Aramco. And all results are published in the paper, leading edge paper in 2011. Here is the information of the publication. First, I would like to show you a 1.5D pre-stack example. Here, the velocity model is consists of 18 layers reflectors, and this section shows you the synthetic data for the modeling procedure. This section shows you the output of the ISS internal multiple attenuation algorithm, and this is also the estimate primary. This section shows the true primary for the modeling procedure directly from the velocity model. And if we go back and forth, we will see the true primary and the estimate primaries are very close. That means the algorithm did a very good job in this test. Then I will show you a very complicated and very challenging 1D synthetic example. For this example, the velocity model is based on the real well-log data, and the model is consists of lots of thin layers, how thin? As thin as 1 foot. So this is a really challenging and complicated case. Here, the left panel shows you the synthetic data, and the middle panel shows you the true parameters for the modeling scheme. And the third panel shows the output of ISS internal multiple attenuation algorithm. If we compare the panel 2 and panel 3, we will see that the true parameter and the estimated parameter are very close. Especially in this very complicated case, we can remove the primary, the internal multiple energy in this region. You see, we have a very clear result here without damage deeper primaries in this region. So that is very impressive. Finally, I would like to show you a field data example. This field data comes from Saudi Arabia, and here I show you the post-stack section. This is the output of ISS internal multiple attenuation algorithm in 1D. And if we go back and forth, we can see we did remove a lot of internal multiple energy in this region and, for example, this region. Because this is the field data, we do not have the true answer, but we can see the difference between the input and the output. In other words, this is the energy we removed from the data. And this result is confirmed by Saudi Aramco interpreter as significantly improved the interpretability. So the conclusion in that leading edge paper is, first, all results are very positive and encouraging. And second, there is no other method that can provide the similar effectiveness for land internal multiple problem. And then even without the effort, my colleagues will show you later how to meet the prerequisites better and how to make the algorithm itself stronger. The ISS internal multiple attenuation algorithm itself has very strong standalone capability. The strong standalone capability is due to very fundamental reason. That is, the ISS internal multiple attenuation algorithm does not need any subsurface information. And thank you. Let's go back to Professor Nicholas.
Thank you, Chair. So we started off this discussion saying that every method has assumptions. ISS methods are no exception. They have their own method, their own assumptions. As Chung just pointed out, the standalone capability of the ISS attenuator is the fact that it does not require subsurface information. It does not mean it doesn't have any other issues. It has that property and separates itself from all other methods for that one single very important property. But it has, when it arrived and in application industry-wide, that this is ISS internal multiple attenuation application. So it's applied CGG, PGS, Schlumberger among major service companies that provide service for both onshore and offshore seismic processing based on the method that this group in its history provided. Inverse scattering series, internal multiple attenuation. And they have, you can read these papers and see what exactly they say is the reason they choose it. So, number one, if you're getting data processed by PGS, CGG, or Schlumberger Western Chico, you are benefiting from a method that was developed within M-OSRP and in our history. A method that, when first proposed, was considered to be radical. Everyone, without exception in the world, who we spoke to, that you can do internal multiple attenuation without subsurface information, said it was intrinsically impossible. Forget about practical. It was just not possible. You needed to have subsurface information for internal multiples. That turned out not to be the case. We are hugely grateful for the people who supported us before I arrived at U of H. The people at ARCO, the people at Schlumberger, the people at Petrobras, the people at the Federal University of Bahia, who gave us a chance in spite of tremendous skepticism within our own colleagues and within those own companies, gave us a chance to show that that is doable. And so you have all this radical inverse scattering series, unconventional, becoming totally conventional and mainstream now. It's a method that's you can get processed in 2D and 3D with the major service companies in the world. So that's very good news and very satisfying and gratifying. The point, though, of what I just started to say is the method has its own assumptions. And those assumptions we're happy to ignore or to understand and not worry about, because earlier on when the method was just getting started, those were reasonable assumptions to make. But without an exception, every day's reasonable assumption today will be tomorrow's obstacle to effectiveness. And the assumptions that are within the ISS internal multiple attenuator today make it ineffective when you have interfering events, interfering internal multiple with a primary. And that occurs many times on land, in the Middle East, in Canada, and often in marine as well. Why? Because in practice, what is this ISS attenuator? It predicts the precise time of an internal multiple and the approximate amplitude. So you have a multiple and you have its approximation, perfect time of prediction, approximate amplitude for all multiples at all depths at once. So what happens in practice is, in order to remove that internal multiple, an indirect procedure is called on, adaptive subtraction, which says that after you adjust the prediction such that after you adjust the prediction and you subtract it from the multiple, you have a minimum energy. Meaning, if you have a multiple and then the multiple is gone, you have less energy than you had a minute ago. You have a multiple and then it's gone. So in some window around that multiple, the energy has been reduced. That is an extremely valuable and essential, was an essential contribution started by Eric Verschuer and Louis Burkout, and we followed, Paolo Cavallo and I, in a global search method for the same objective, energy minimization. And it has a long record of contribution. But when you come to interfering or proximal events, that is totally inappropriate and will cause harm. If you have a primary that interferes with a multiple, you can have destructive interference. You saw a primary and a multiple completely destructively interfering. There was nothing, no energy there when the multiple was there. And when the multiple was removed, the energy went up. You got a primary. In that earlier analytic example, that hidden primary. So the criteria itself, which has been so depended on by industry, adaptive energy minimization, adaptive subtraction, is a good method when you have a multiple isolated and the prediction away from other events. If it's proximal to other events, that criteria, let alone how you apply the criteria, is inappropriate. You need a new criteria. So since this group accepts the responsibility of recognizing and addressing current challenges, which means how do you get, for example, that North Sea example of Total, where you have all kinds of 1D generated multiples all interfering with primaries. How are you going to deal with that? You cannot rely on internal multiple ISS attenuate plus adaptive. You can't. You have to respond to that by this strategy that we've defined. So in addition to being not an eliminator, that one term, when you have many generators, can produce what's called spurious events. Those spurious events are false events for that one term, that ISS internal multiple attenuator. They are completely purposeful from the inverse scattering elimination point of view. There are higher order terms in the inverse scattering elimination process that expect that those false events, require them in fact, in order to carry out their purpose. So two parts of the current ISS internal multiple attenuator need to be addressed. We need to turn the attenuator into an eliminator, meaning make the time exact and the amplitude exact, equally effective at every offset. So that's what this says. And get rid of spurious events. Provide the prerequisites. Separate the scattered wave from the reference wave. Deghost your data. And last but not least, you need to, and that item 2 is a big issue for land. And Jim will be talking about that. How do you separate the scattered and reference wave? How do you do deghosting for land? Land on top of land, how do you do it for buried sources and receivers? If you're going to be doing all of these multiple removal and subsequent procedures for buried sources and receivers, these prerequisite satisfaction on land is a big project within M-OSRP. In the marine case, this is mature. In land, it's new, embryonic, needs attention, needs nurturing, okay? Needs time. Okay? So the third is we need to develop a set of adaptive criteria to replace energy minimization that are derived from the algorithms they're meant to serve. They're properties of the algorithm. So because I don't care whether you satisfy all the physics requirements, scattered wave and reference wave separated and deghost, and you remove the wavelet. There are things in the real world that you didn't put into the physics when you wrote down your equation. The air-water boundary is not flat, it's not -1. The cable's not flat, it's feathering, there's finite sampling, there's finite aperture. All of those issues, you need a dial. You need a dial to address the part of reality that you have not accommodated in your algorithm. And that is where we feel indirect cost functions have an appropriate role, and we feel you should derive those new adaptive criteria from the methods they're meant to serve. Find a property of the method and drive the solution to satisfy the property when you don't have perfect conditions that match your physics. The physics is not a problem. It's your physics that you've written down is not reality. Never is, never will be. You need a dial. That's what that third item is talking about. Okay? The dial for things that are in the real world that are not in what you wrote as physics. Okay. So now we're moving to what are we going to do to provide the new level of necessary effectiveness. We're happy with all this ISS, internal multiple attenuation. As I just said, it is standalone today, but when you have interfering primaries or multiples, or you have spurious event generation, which many generators will cause, it is not acceptable. If you say, I have a multi-dimensional generated internal multiple and I need to eliminate it, the answer is, we don't have one. The world doesn't have one. From a multi-dimensional Earth, I need to eliminate an internal multiple. That's an open question. The only place that that will come is from the inverse scattering series. The only place. That's one of the things we're after. There was discussion of it in Adriano Ramirez's thesis. Wilbur Herrera made some substantive progress, and now you're going to see Yang-Li Zhao showing you a 1D version of internal multiple elimination and the difference between attenuate and eliminate when you have proximal interfering events. Yang-Li?
Thank you. Hello everyone. I'm going to show you the recent progress of the internal multiple elimination algorithm for all reflectors for a 1D Earth. As we know, the ISS internal multiple attenuation algorithm has standalone capabilities. It can predict all internal multiples with correct time and approximate amplitude at once. And it's a 3D algorithm. and it doesn't need any subsurface information. However, it has the attenuation algorithm has two limitations, and we can address those limitations and improve the algorithm. The first limitation is it's an attenuation algorithm, not an elimination algorithm. If the primaries and the internal multiples are isolated, we can remove the attenuation. We can remove the internal multiples by using the attenuation algorithm. But however, if the primaries and the internal multiples are proximal or interfering with each other, then the criteria of adaptive subtraction may fail, and it's better to use the elimination algorithm to remove the internal multiples. And the other limitation is the spurious events prediction. My colleague Chao Ma will talk about how to address this limitation. Here's a model I used to test the internal multiple elimination algorithm. It's an elastic model with 4 reflectors. And here shows the input data. Here is this shows the PP data. And those red arrows pointed to the P primaries. And those green arrows pointed to the converted primaries. And these blue arrows pointed to the P multiples. And then I'll show you a section of in the data. In the first picture is a section of the input data. And in this section, there are 3 events. And here, this blue event is an internal multiple. And here, this is another internal multiple. And they are interfering with a primary. And this is a converted primary. Because it's a converted primary, it has relatively low amplitude at near offset. And the second picture shows the attenuation algorithm prediction. We can say the attenuation algorithm predict correct time and approximate amplitude of all the internal multiples. And the third picture shows the prediction from the elimination algorithm. And we can say the elimination algorithm predict both correct time and correct amplitude of the internal multiples. Because this is a synthetic data, we can generate the primaries only. So in the fourth picture, here shows the actual primary in this section. And then we can subtract the prediction from attenuation algorithm and the elimination algorithm from the input data. And figure 5 shows the prediction, shows the subtraction result for picture 1 and picture 2. We can see the internal multiples has been reduced, but there is still some residues. And we can see the last picture, the 6th picture, shows the result after subtract the elimination algorithm from prediction from the input data. We can see the internal multiples has been completely removed, and the primaries has been recovered. As you may notice that there are some numerical issues at the near offset, and now we are working to improve the prediction at the near offset. And here's a few reference for the internal multiple elimination algorithm. Thank you.
Thank you, Yang. So Yang just showed a very impressive result on the difference between the current industry high watermark of capability, the inverse scattering series internal multiple attenuation, and his inverse scattering series internal multiple elimination for 1D Earth, and how in particular important it was when you have interfering and proximal events. The other part of the limitation of the inverse scattering series internal multiple attenuation is, as I mentioned, that algorithm on its own can create false events. The inverse scattering series internal multiple elimination series does not have a problem with those events. Those events are in fact needed for other purposes, and other terms in the inverse scattering series elimination series will anticipate that limitation of one term, and they act to remove that issue. So Yang Li Zhao is addressing issues of turning an attenuator into eliminator, and now you'll see Chao Ma describe how spurious events are removed by using higher order terms in the inverse scattering series. Chao?
So thank you for Dr. William's introduction. Good afternoon, everyone. Thank you for this opportunity for speaking. So in the last presentation, my colleague Yang Li, he developed an ISS elimination algorithm, shows very impressive results. So that is one aspect of bringing the new capability of the algorithm itself. So in this presentation, I'll focus on another aspect, which is addressing the false event prediction by bringing new more terms from the inverse scattering series. First, this false events prediction was first pointed to us by one of our sponsors. In that test, that's a very successful test. But deep in that prediction results, they noticed some false event prediction. So that's how this problem came to us. That's a real problem. So earlier, so the way to understand the false events prediction is as follows. So recall earlier in this video that Dr. William mentions the amazing cooperative nature of between the different ISS terms. He illustrated that cooperative nature using an example in the ISS free surface case. So the lesson there is what appears to be a deficit. It turns out it's actually purposeful from the point of view of the inverse scattering series. So that lesson also applies in the ISS internal multiple case. So in other words, what appears to be a deficit in this case is the false events prediction is totally anticipated by other terms in the ISS. So basically what we did is we located those terms which fully anticipate this issue and provide a resolution from the other term within the inverse scattering series. So in the next, I will show an example to showing the improvement by addressing the spurious events. So here is the model we use from the solid RAM code. We can see there are many reflectors for this test. We use this model to generate our test data using reflectivity methods. So in the next two slides, I will show two prediction results. One is from the current algorithm without addressing the false events prediction, and the other one is the prediction results with the addressing of the false events prediction. And we will compare these two prediction results with the actual internal multiple to see the improvements. So let's first compare the prediction results with the actual internal multiple in this slide. Here in this slide, the blue line represents the actual internal multiple in our data, and the red line represents the prediction results from the current algorithm without addressing the false events prediction. We can notice there are mismatch between the actual and the prediction results. Next, we will see the prediction results with addressing of the false events. So we can see where the black arrow points to the place where we have the great improvement. I will flip back and forth to see the difference. So here is the results without addressing the false events prediction. So here is the results with addressing of the false events prediction. So in this example, we can see we have many reflectors, and the events are all interfering with each other, and we can not explicitly see which one is a false events. But how we can say the false events are there, because when we include the terms that intended to address the false events prediction, and we can see from the results, the prediction results actually improve. So we can see even though we don't know which one is the false events, and when we apply the algorithm that intended to improve the results, the improvement is there. So there here we show the three main takeaway points from this brief presentation. So we provide a new algorithm from the term in the ISS to address the false event prediction. And actually, as mentioned earlier in the Dr. Wiggins' comments, so it can be shown that when you have many reflectors, addressing the false events is very significant. For example, in the Middle East or North Sea, where you have tens, hundreds, or even thousands of generators, the chance of not having the false events prediction is very low. That is to say, in that chance, applying this algorithm that intended to remove the false event prediction is very significant. And let's say in some rare case, when you don't have the false events in your prediction result, but you still apply this algorithm, applying this algorithm will cause no harm. So that's also a very important point to remember. So in this presentation and the last one, we focus on some innate issues of the current ISS internal multiple attenuation algorithm. And we show how we can include more ISS terms to improve the capability. And besides that, we can also have prerequisites of this algorithm. In other words, pre-processing, for example, separating the reference wave from the scattered wave and deghosting. And in the following presentations, my colleagues, they will cover more aspects on that. And thank you.
Yes, excellent job. And very impressive. In other words, those false events, as Chow just pointed out, you don't even know, even after, where they work. It's such a jumble of interfering primaries, internal multiples, and false events that you can't identify anything as false. The algorithm doesn't need for you to identify. It removes them. That's amazing. That is truly amazing. Okay. How do you know it's improved? Because in the synthetic, you know what the multiples are, and you can generate them separately. So it shows under extremely complicated circumstances. This was, as Chow said, Yi Lo pointed this out to us first. They were seeing deep down in the sections in the Saudi Aramco results. They were very happy, as Chung Fu said, but they saw occasionally some predictions that were not real. And that generated this interest. You tell us that's the problem. We are here to find out a solution to it. Yes. And so, Chow, very impressive. Okay. Okay. As Chow mentioned, Dr. Jinlong Yang will now be talking about the effect of these prerequisites, explicitly showing the effect of these prerequisites that we talk about, like deghosting, for example, on the effectiveness or lack of effectiveness of these algorithms for two reasons. One is that they're valuable in themselves. If we want that kind of effectiveness of doing those separated wave Green's theorem forms, if we're committed to effective multiple removal onshore, we must have the kind of prerequisite satisfaction of ghost removal and source radiation pattern accommodation that Dr. Jinlong Yang will show. He's showing it in a marine setting, but the lesson is certainly for marine, but is an issue which is a major project here. How do you do the pre-processing for either surface sources and receivers onshore, and also for buried sources and receivers for 4D application? So look forward to your talk.
Thank you for Dr. Wagner's introduction. And as mentioned, the prerequisites are very important for our multiple removal and seismic imaging and inversion. Here I will talk about the impact of prerequisites on the multiple removal algorithm. I will show two examples. First, I will show the impact of ghosts for free surface multiple removal. And the next example is I will show the impact of source radiating pattern on the multiple removal. First, the first example is the impact of ghosts I want to show. This is one water bottom layer model. The source at 7 meters and the receiver at 9 meters. And next, I will use Carnier-Hooper method to generate the data. If we have ghosts in our data, the three events are generated. First is the primary and the free surface multiples, and along with them there's a ghosts. If we have ghosts in our data, it means that it's not satisfy the prerequisites of the free surface multiple removal. If we use our current inverse scalar series free surface multiple elimination algorithm to predict and remove these multiples, this is the result. The middle panel is the prediction, and after remove the free surface multiples through a simple subtraction, the right panel is the result. As we can see, after removal, the multiple can be worse. It means without deghosting, the multiples cannot be removed. If we deghosting first, it means the data only consider primary and free surface multiples. We still use our current algorithm to predict and remove free surface multiples. We can see after simple subtraction, all the free surface multiples can be removed completely at all offsets. It said after deghosting, our algorithm works very well for this data. Next, I will show an example for the impact of source radiating pattern on the free surface multiple removal. Here it's a similar model, but this time I put the very shallow water bottom. This data will have interfering events. The interfering events can occur in marine environment, can often happen in onshore application. Here, only the primary and the first order free surface multiples are generated. As I said, it's a very shallow water, so the primary and the multiples are overlapping at a large offset. The right-hand side is a wiggle plot in the box part. As we can see, the primary and the free surface multiples are overlapping and they cancel a lot. If this data are generated using a radiating pattern, the source with a radiating pattern. So if we still use our current algorithm, it assumes that the source is an isotropic point source. What will have? This is the result. After free surface multiple removal, if we do not consider radiating pattern in our algorithm, this is the result. You can see there's a lot of residues. How do we know this is residue? Because this is the synthetic data, we can generate the primary only, so we can compare the result. This is the generated primary only. I flip back and forth. Look at the right-hand side, or first look at the left side. You can see the residues, and then look at the right side. This is using current algorithm. This is free surface multiple removal. This is the original primary. We can see there's a lot of residues in the red circle part. And also, the primary is a little weaker than the original primary. If we incorporate the radiating pattern in our free surface multiple elimination algorithm, this is the result after free surface multiple removal. we can still compare with the primary only. We do not see any difference. We can pick one trace to look at the detail. The red line is the original primary generated primary, and the blue line, if we use the current free surface multiple elimination algorithm. After the free surface multiple removal, we can see this is some residues over here, and also the primary is a little weak than the original primary. If we use the modified algorithm, that means we incorporating the source radiating pattern in our algorithm. The green dashed line is the result. We can see it matches the original primary very well. From these two examples, we can see providing the prerequisites, deghosting and incorporating the source radiating pattern is very important for our multiple removal algorithm. This is the free surface case. Also, similarly, in the internal multiple case, this is also very important. And the RSS elimination algorithm assumes that the RSS attenuation algorithm is effective as an attenuator, including effective reference wave removal, deghosting, and compensating for the source wavelet and its radiating pattern. This is for marine case. Also, to achieve this prerequisite on land, the green theorem pre-processing method is also developed and applied by my colleague Jing Wu. He will talk her results in the next talk. Turn back to script. Thank you.
Excellent. So this has work that Dr. Xinlong Yang just showed has important implications, very important implications. As always, we don't have a method that is the method. We're just always trying to add to the toolbox of opportunities. So if you have a free surface multiple in the marine setting, and you didn't do deghosting, and it's all sitting by itself, then you don't even need Cavallo. You can go to SRME and do adaptive subtraction. If you have shallow water and interfering free surface multiple and a primary, which can happen with many orders of free surface multiple, then that reliance on the adaptive subtraction, as we know, the whole criteria fails. And you have to have not only the Cavallo free surface multiple algorithm, which given its prerequisites is equally effective, gives you the exact amplitude and phase of the free surface multiple, but as Dr. Xinlong Yang showed, it will not produce that exact amplitude and phase at every offset unless it gets its prerequisites. So if you have a proximal free surface multiple and a primary or another multiple, you need surgical removal. And the lessons that Dr. Xinlong Yang just showed us are in your toolbox. You select that. If you think you have a multiple sitting by itself, then that's not the appropriate choice. You can use a more blunt instrument. You need these more subtle, sophisticated, and capable methods when appropriate. So that's a way of describing. And as Dr. Xinlong Yang said, this motivates that importance of the prerequisites for prediction effectiveness is important. And if we're serious about multiple removal on shore, we have to have those prerequisites. And so this is not only, Dr. Xinlong Yang not only is showing prerequisite, he is the prerequisite for Jing Wu, who's going to take us on shore and show how those prerequisite satisfaction, those wave separations, is being pioneered by her work. Okay?
Until now, we have seen the wave separation for offshore and seen their importance for the multiple attenuation and elimination. And we have also seen the impressive result of internal multiple attenuation for onshore. So now if we want to have internal multiple elimination for onshore happen, we also need a set of pre-processing. Say we need to separate the reference wave from the scatter wave. We also need to remove the ghost. Well, in this talk, I'm very happy to show you how that is realized by using the elastic Green's theorem. Okay, this talk will first give you the reference and the scattered wave separation, and then it will give you the deghosting of the scattered wave. Okay, first let's look at the first part. And from this line data example, we can see the ground roll is very strong and seriously contaminate the reflection of the scatter wave. And we are trying to identify and remove these waves. And the linear method like FK could be chosen, but those kind of methods may damage the reflection. So alternatively, here we'd like to use the wave theory based method to achieve this goal. And we have seen the Green theorem has shown its capability for wave separation for marine case. And by this process, next in this part, I will show you how to use elastic Green theorems to achieve wave separation for land. And we realize in the major issue of wave separation for land for both on surface and buried sources and receivers is the near surface complexity, and is time varying and unknown. And we are committed to address those kind of issues. But here in this first part of the talk, I just assume we have the near surface to be homogeneous, elastic, and known. And our wave separation method in this part is within this assumption. Well, let's just start from this. And there are other activities and plans within our group to address the other issues for more realistic situations. Okay. Given this assumption, we will have our experiment onshore, and we have our model to be air and then homogeneous near surface, and then suddenly to be unhomogeneous marked with this dark brown. And again, we assume the Earth right below the free surface is known. And this is our experiment. And here we choose the reference medium to be half space air over half space elastic separated by the free surface. And now if the reference medium is agree with the actual on and above the measurement surface, then we will have these two sources. And the first source is the active source. It will give you the reference wave. And on the other side, the second source, say the Earth's heterogeneity of these marked by this dark brown, will give you the scatter wave. Okay, for the reference wave from the first source, you will have the direct wave. You will also have the surface wave of all the ground roll, and these waves are exactly we wanted to separate. So next, let me use some mathematics to show you how do we have our wave separation method. And these are two wave equations. The first wave equation is used to represent the actual wave field. And here phi is the actual wave field, the total wave field. It contains both P and S components. And L here is the differential operator representing the property of the actual medium, say representing the air and then some homogeneous near surface and then the heterogeneous Earth. So for the right side is the source term. Here we have the P source only. And the second wave equation is used to express the impulse response of in the reference medium. Here G0 is the corresponding Green's function, and L0 here is the differential operator representing the property of the reference medium, say half space air over half space Earth, half space elastic Earth. And the source side we have both P and I source. And by combination of these two wave equations and then apply the Green's second identity, we will have this integral formula for the wave separation in X omega domain. And this is for a 2D case. And applying this integral formula, we will have either have the phi 0 or the reference wave, or phi s, which is the scalar wave based on the location of the output point R or the prediction point. Let me explain here. If we put the output point R below the measurement surface, then the surface integral will give you the reference wave. Otherwise, if you put the output point R above the measurement surface, then the surface integral will give you the scalar wave. Okay. Let's back to the formula. If we want to apply this integral formula, we can see we need to have phi and its gradient. We also need G0 and its gradient. So actually, for land measurement, we measure the displacement, and for a 2D case, the displacement will contain both x and z components. So now we need to apply the divergence and the curl on the displacement to obtain phi, and then we put phi into the integral formula. Okay, next, for the Green's function, you can see this Green's function is in terms of R prime and R in this air and elastic reference media. So we know, for example, first, if we wanted to obtain the reference media, reference wave, we need to put R below the measurement surface. So that's the reason why this Green's function have R is deeper than R prime. Okay, next below is the wave equation representing the Green's function. And with this wave equation, the Green's function will contain two parts. The first part is the direct wave, say the direct P from P source, direct S from S source. And the second part is the reflection caused by the existence of the free surface. And you will have the incident P and then the reflected P and S. And then also the outgoing S will give you the reflected P and S. So until now, we have obtained phi and G0. We can exactly apply those integral formula to separate the reference wave and the scalar wave. And until now, there's no assumption about the measurement surface. So it can be flat, horizontal, or not. It can also be rolling, and there's no assumption. So if here we assume the measurement surface is horizontal, we can further transform the integral formula to Fourier domain to be like this. And the tildes here represent all these terms are in Fourier domain. And on the right side, the z prime is evaluated at the receiver steps. Okay, by applying the formula in X omega domain, we can just make the output point R on the measurement surface to separate exactly the measured total wave into reference wave and scalar wave. In other words, we can obtain either the reference wave of the measurement data by choosing the R to be belonging the volume below, or we can obtain the scatter wave. We can obtain the scatter wave of the measured data by choosing this R to be belonging to the volume above. And but for either case, what we separate is exact portion of your measurement data. Okay, next, let me use one example to show you how Green's theorem works to separate the reference wave and the scatter wave. And these tests have R on the measurement surface. In other words, we just apply the formula in kx omega domain. And this is our model. Here we have air and then the two-layered Earth. And given this model, we put our source on the free surface, and this is a P source. With this P source, you will have both P and S components on your measured data. Okay, and again, we locate the output point on the measurement surface. And now we obtain the data with both P and S components, and we have the corresponding Green's function with those two parts. We can apply the formula to have our prediction result. Okay, next I will only show you the result of P component, and the S component will have the same conclusion. Okay, this is the total P wave field. And from this picture, we can see the direct wave and the strong relay wave. And we can also see the relatively weak reflection data. And this data will be put into the reference and the scatter wave separation algorithm. And first, if we choose the output point on the measurement surface to be part of the volume below, then applying the Green's theorem, we can have the separated reference wave. And this picture shows you the predicted P component of the reference wave. And let me remind you here, this result is from Green's theorem using both phi and its gradient on the measurement surface. Now we can compare this prediction result with the actual reference wave in the data. We can see both their phase and amplitude are matching very well. Okay, so second, if we choose the output point R on the measurement surface to be part of the volume above, then we will have this prediction result. Say we will have the separated scatter wave, and this picture shows you the predicted P component of the scatter wave. And again, this result is from Green's theorem using both phi and its gradient on the measurement surface. Okay, with this example, you can see the elastic Green's theorem can give us the satisfying result to separate the reference wave and the scatter wave. Okay, once we, after the reference and the scatter wave separation, we will go to our next wave separation step to deghost the scatter wave. We know the scatter wave contains both the upgoing wave and the downgoing wave. What we are doing next is trying to separate the downgoing wave from the data and leave the up wave only for the subsequent processing. Okay, and we have this same experiment, but for this time the reference medium is chosen to be homogeneous elastic in the whole space. And given this reference medium, again we apply those integral formula and evaluate above the measurement surface, we can have the deghosted scatter wave, or to say we can have the upgoing wave. And since we use these homogeneous whole space elastic as the reference medium, the Green's function only contains direct wave, say direct P and direct S. Okay, again, I'd like to remind you, since here we like to obtain the ghosted wave, so we needed to put the output point R above the environment surface. So that's the reason why R here is shallower than R prime. Okay, next I'd like to use the same model to show you how to deghost by using the Green theorem. And here we still use the P component data here, and this is the scattered wave, the P component scattered wave, and this wave contains both the downgoing wave and the upgoing wave. And this data will be input to the deghosting algorithm. And now if we choose the output point R on the environment surface to be part of the volume above, we can have this prediction result. And this is the deghosted P component of a scatter wave. And this result is also after applying the Green theorem using phi s and its gradient on the environment surface. Okay, so here we'd like to evaluate the accuracy of this result. So I just create the deghosted data. Say we have the model, we can just generate the upgoing wave with some analytical form, and we can treat this one as somehow the accurate data, and we compare this accurate result with the result from the Green theorem. You can see it's hard to see difference. And again, with this example, we can see the Green theorem can effectively remove the ghost. Okay, at the end, I'd like to have some discussion of this method. And this method have a data requirement. And let's review this integral formula. Here we can see we need the total wave and its normal derivative if we wanted to separate the reference wave and the scatter wave. And second, we will need the scatter wave and its normal derivative if we wanted to remove the ghost. And alternatively, if you have the source signature, we can use the source signature to replace the requirement of the normal derivative. And again, so to obtain the data in PS space, we need to transform the data in displacement space by applying the curl and the divergence. Say we need for both x and z components, we need their derivatives along horizontal and vertical directions. And next is, for this talk, we just assume we know the reference medium and assume it's homogeneous. And as I mentioned at the beginning of this talk, we know the major issue of the wave separation is the complexity near surface. So there are some plans and ideas within our group to address this problem. First, my colleague Lin Tang has used the invariance criteria to back out the near surface properties. And the second, Dr. Wegland is right now developing the wave separation method for buried source and receivers without knowing any information above, below, or at the measurement surface. And let me give a summary. So we show you the elastic Green theorem here for onshore application. And with this method, we can remove the direct wave, including the ground roll, without damaging the reflection. And we can also remove the ghost. So at the end, what we are doing here is trying to provide the effective prerequisite for internal multiple elimination for onshore. Thanks.
Very good. So, as Xinbu said, the motivation for this is we're committed to improving and providing and delivering effective methods for multiple elimination offshore and onshore. As Chung Fu showed, the ISS internal multiple attenuator is the most effective method today available in industry that you can process your data with. And it comes from this group and its history. If, however, onshore you have an interfering primary and multiple, you need an internal multiple eliminator and spurious event removal. In order to achieve that, those pre-processing steps start to matter. And what Jing-Woo just showed is how do you do those wave separation early steps in that tree of separating the reference field from the scattered wave. The reference field is much more complicated on land than it is in the marine setting. It has ground roll, as Jing-Woo showed. Ground roll and its removal is a non-trivial issue all by itself for our sponsors. We hear this from them. They're looking for better methods than their current approaches, which can damage the reflection data, and they're not interested in that. They want to remove it and preserve the signal, preserve the scattered wave. In addition, if you're interested in any kind of broadband on land, you want to be able to deghost your data for whatever the purpose is. Yes? All the multiple removal methods need those set of wave separations before they get started. And if you can't rely on adaptive to fix up your problems, and we're assuming you can't, because where you can fix things with adaptive plus our current prediction is not good enough for the current challenges that our sponsors face with interfering and proximal events. So that's a very important contribution and very impressive results. So as Jing-Woo mentioned, in her first test, naturally enough, she is assuming, Jing-Woo is assuming, that she has air and the reference medium is air and a known homogeneous elastic medium which agrees with assumed homogeneous laterally invariant near surface onshore. As Jing-Woo said, she's fully aware of the real problem, but you have to start with the simpler problem. How would you even do it? How would you do those wave separation procedures where you didn't have that complexity? As Jing-Woo mentioned, there was work from an earlier student, Lin Tang, where you use a quality of the reference wave predicted under the cable, that if the reference wave is a wavelet times the reference Green's function, then for different points that you evaluate the reference wave, it should give you the same wavelet, which you just subtract by a different Green's function between your source location and your output point. And the wavelet should be the same if you have the accurate reference properties in the near surface. If you don't, you will see the wavelet is predicted at with different values at different output points as an indication, an indirect indication that you don't have the right reference medium. That was the work of Lin Tang. I'll just show you results. So this is prediction of the wavelet with that wave field prediction, wave field separation getting the reference wave in the case where you had the correct reference velocity. Here's where you had an incorrect, or further incorrect. It should be invariant. It should be the same wavelet at every output point if you had the right reference. So that's a now what Lin then also tested is what if you didn't have an isotropic source? If you don't have an isotropic source, by definition, the reference wave should not be the same in different directions, but you should have the same amplitude, the same function for a given ray, for a given angle. So you can compare at different output points along a given ray whether you have an invariance. So, I'm sure you can see what's going on here. What's going on here is there's a radiation pattern. Here. So the wavelet, if this was isotropic, just a point, there should be invariance here. But it's not isotropic. So at every different point, you have an effective different reference wave. So if you treat it as being invariant horizontally in the presence of a radiation pattern, it should not be the same. But if you look on a ray, a given angle, it should be if you have the correct reference velocity. So there, you see those difference in the wavelets. Okay, that's not an indication you have the wrong reference velocity. That's an indication you assumed an isotropic source and it's not. Yes. Then goes along a ray. Yes. Assuming now that she has a radiation pattern, and every point on that ray gives the same wavelet. Okay? So that's an idea of trying to back out from some property of the prediction itself what its own near surface properties are. So we'll leave it with that, and that's certainly something we will pursue for onshore and on the surface measurements. Next talk is by Jinglu Lin, who's going to discuss the significance of having the correct dimension of the source independent of the dimension of the Earth. Okay? Jinglu, look forward to talk.
Many thanks to Dr. Wittlein for the introduction. And it's my pleasure today to give a brief presentation on how significant to incorporate a 3D source in our ISS internal multiple attenuation algorithms. And the lessons here is that, as shown by my colleagues, and the ISS internal multiple algorithm itself does not care the subsurface information and the Earth model type, but it does care the source dimension you assume. Okay, and as we all know, there are onshore and offshore regions which are close to 1D Earth and have serious internal multiple problems. For example, Central North Sea, Canada, and offshore Brazil and the Middle East. And here, to develop a more realistic and complete algorithm, we incorporate a 3D source into our ISS internal multiple algorithm. The message here will show you how important it is to incorporate a 3D source in the algorithm, and the results here will demonstrate that by comparing a ISS internal multiple attenuator for 1D Earth pre-stack and assuming a 2D line source versus a 3D point source, and where the data comes from a 3D point source. I will show you what the difference will they make. This is the model we use to generate the data, acoustic data pre-stack, and assume a 3D source in it and 1D Earth without free surface. You can see the data contains 3 events, 2 primaries and 1 internal multiple. Here, let's extract 1 trace from the data and other predictions to compare them. And the right, you can see 4 lines in this figure. The right line here represents the data generated by a 3D source and 1D Earth. And the blue line here represents a prediction assuming a 2D line source. The black line and the green line in this figure are both the predictions assuming a 3D point source. The difference is that the Hankel transform in our the prediction assuming a 3D source involves using in our prediction prediction assuming a 3D source involves a Basel function, but the asymptotic Basel one, which represented in this green line, is an approximation to that, which makes the computation more simpler. And that's zoom in the parts in this red box to check the internal multiple events and the predictions. First, the red line here is our original internal multiple data. Here, the data comes from a 3D source. And the blue line in this figure is a prediction, internal multiple prediction assuming a 2D line source. We can see here the amplitude of this prediction is much bigger than the original internal multiple event. And what will happen if you subtract this kind of prediction from your original data? I will show you. Okay, here the purple line represents the result after subtracting the 2D source, the prediction assuming a 2D source from the prediction assuming a 2D source from our original data. You can see that you have the possibility to make this problem harmful, and this result after the subtracting gives you a larger event in the opposite direction. And what if we incorporate a 3D source in our prediction? Okay. The black line in this figure here represents the result of the internal multiple prediction assuming a 3D source. You can see here the amplitude of this prediction is a little smaller than our actual internal multiple, which means it's attenuator. And in that case, if you do the subtraction from your original data, you can always reduce the energy of the internal multiple. And the next line in this green color is as we stated before, is a prediction assuming a 3D source, and also use an asymptotic Bessel function unit. And this prediction will reduce the computational cost and produce a very positive result at this far off site, which means it's close to this attenuator prediction. And until now, we can see that all the predictions assuming a 3D point source can give us can always attenuate or reduce the internal multiple in our original data. Let's start the conclusion here. For 1D, 2D, or 3D subsurface, it's always important to use the ISS internal multiple attenuator algorithm with a 3D point source. And it also helps the ISS internal multiple eliminator, which is pioneered by my colleague Yang Lei Zhou. Thank you.
Thank you, Shimon. So the conclusion is that if you do synthetic data and you have line source data and a 2D Earth or a 1D Earth, no problem if you're synthetic data. But if you're doing real data is going to come close to a 3D source. And independent of the dimension of the Earth, that might be appropriate in that given plane. The need for incorporating a 3D source in your attenuator is critical because, as Jinglu showed, if you assume a 2D source in your attenuator and the data comes from a 3D source, the prediction can make the multiple worse. Doesn't reduce it, makes it worse. And there's nothing worse than that, making problems worse, which is not part of our program. Thanks. Okay, so we're pretty well far down this tree, where now we've separated primaries from free surface and internal multiples. And now the question is, what are you going to do with primaries? It's maybe worth stopping for a second and saying a word quickly about the history of seismic processing. In multiple removal, the first method for reducing multiples was called stacking. If you have the velocity of primaries and you stack your data, you will suppress multiples. That was a early and important method for suppressing multiples. Then you had FK filters, you had radon, you had high resolution radon. At each stage in that evolution of more capable multiple removal, you needed an increased capable velocity model. And then it came to an end. Those methods were 1D, they needed a velocity, and you couldn't deal with interfering primaries or multiples, but you needed to have some move-out difference in order to separate them. Along comes inverse scattering series, and suddenly you have an ability to do free surface and internal multiples without velocity. And all the work that you've heard in this review up to now shows you what the capability is, that standalone delivery, and what our plans are for further delivery within the inverse scattering series for multiple removal offshore and onshore without subsurface information. So in the history of processing primaries, there's a similar evolution. You had post-stack time migration, post-stack depth migration, pre-stack time migration, pre-stack depth migration, reverse time migration. That's a quick way of talking about the evolution of processing primaries. And each step in that evolution, the migration method became more effective, more able to deal with realism in the earth. But there was a commensurate, at every single step, increased need for more accurate velocity information. If you went from time migration to depth migration, and you didn't have a more accurate velocity or an adequate velocity, depth migration would be worse than time migration if you didn't have an adequate velocity. So here we have this evolution of multiples, which at some point went to the inverse scattering series to develop fundamental new capability that didn't require subsurface information. Here we have this evolution of primaries, which step by step needs more subsurface information to be more effective. And then we have John Etchen's comment that today the biggest obstacle in his view, in his considered view, to seismic processing is the inability to effectively produce an adequate velocity. That's a statement that happened at the last SEG. Given that, and there is no candidate method for providing an adequate velocity, it's reasonable to then think, and we have been thinking and working on using the inverse scattering series to find a direct way to do depth imaging without needing, knowing, or determining the velocity. So that's the next topic we're going to discuss. Taking the step that multiples went from all these increased need for velocity methods to suddenly not needing any. Now we're talking about moving from all these imaging methods which have an increased need and inability to provide that need. And no, it's not just a candidate. There's no, forget about a credible candidate. There's no candidate with the potential today to move the velocity analysis from what it is today to what it would need to be. Forget about credible. There's no candidate, period, to move the gap from what tomography, common image gather, and FWI can provide to what is needed. We have no possibility. Okay? There's no, I'm not saying it's not possible, we just don't have a candidate. Given that, it's reasonable to look at the step that happened with multiples. So that's this topic, depth imaging without a velocity model. And it's been going on for a while. It's a tough problem. The inverse scattering series says that's achievable directly without subsurface information. Takes a lot of turns, a lot of ingathering. So you'll see the progression of that capture. This is an early historic result with from Simon Shaw, who won a Carter Award for this. He's at ConocoPhillips in Aberdeen. This is a velocity model, 1D, normal incidence. This figure in the middle is a water speed stope migration of primaries from that velocity model. We're assuming that all of the people who spoke before me today have been effective and successful, and we don't have a problem with multiples. In everything that the inverse scattering series does for depth imaging, as well as conventional imaging, the assumption is you're dealing with primaries. And the same here. The movie on the right shows you what happens to the inverse. Should show you. Thank you. So this shows what the inverse scattering series depth imaging subseries, which only looks at moving, not changing the amplitude for transmission effects. Just move the mislocated image given water speed to its correct location. And that movie corresponds to different terms in the series, in this case 67 terms. And what you'll notice is, the amazing thing is this stops being agitated. This remains in need of more help because it has a bigger error in its location than this one has. When this lowest reflector stops activity, notice that this one's happy, and above that's still not happy. They need more conversations, more terms. When this is happy, it stops talking. In other words, the inverse scattering series, at any given depth, it determines whether there's a need and how many conversations it needs with those above it, how much assistance it needs until it's satisfied. And it decides when it's satisfied. So here's the pre-stack version of that same, which is very important. You see these yellow are the actual depth. You see this pattern here. Is it narrow? Yep, it's narrow. Again, this is common image gather flatness with no distortion that occurs, and it stops while these are still having conversations with shallower events trying to correct this mislocation. This is not stripping, this is not finding a velocity, this is a set of communications exactly like multiple removal, exactly like multiple attenuation and removal of data multiplying data. There are primaries here multiplying and communicating with shallower primaries on a task which is set for them of finding their correct location, period. They don't ask for, nor are they provided, nor do you know before, during, or after any velocity or any other information. This is Professor Feng Lu's example when he was as an intern at ExxonMobil. Big contrast, lateral bearing. This is the water speed image. 1, 2, 3, 4, 5 images in red. 1, 2, 3, 4, 5. This is here. This is the first term. This is a water speed slope migration that gets input into Professor Feng Lu's algorithm, closed form, and you get a much improved 1, 2, 3. And this is now the new image of this. Not perfect, but this was a early gathering of terms. The gathering of terms for ISS depth imaging is at the beginning. It is not, there are many more terms that still need to be gathered, and you'll see examples of where the need for more terms exists. This is Zicheng Wang, a student after Feng Lu, with more terms, and you see an improvement here. These algorithms are lightning fast. They take 30% longer in time than a single water speed migration. I'll repeat that. This picture takes 30% longer in time than a single water speed migration. A single water speed FK migration is free. It's so fast, lightning fast. Okay, this is a fog shadow zone. This is the water speed migration. 1, 2, 3, 4. 1, 2, 3, 4. This guy is here. This belongs here. Of course, the top reflector is where it belongs because you have water speed. And this is Feng Lu's collection of terms, and this is Zi Cheng's further collection of terms. You can see there are terms here in the inverse scattering depth imaging capability that are not within the algorithm yet. I'm going to skip this math and just show you some recent results from Feng Lu. The red here this is a Mamouzi model, and you have these colored lines indicate major reflectors. These are the parameters of the model. This is a shot record from the center of the model, and here you see something very impressive. This green is an actual reflector, and in each case, the blue and so on, those are pointing to actual reflectors. This is what water speed does for that. This water speed image goes to that, okay, without any information about the velocity. Okay? So these are different angle information. In other words, different subsets of the data giving different information. Here's three different places where we're focusing on. The capture of terms in the inverse scattering depth imaging subseries to date are dealing with terms that exist in a 1D Earth. There are certain terms that are exclusively arise for lateral varying Earth. Those terms have not been fully incorporated, yes? So there is a whole plethora of terms of depth imaging capability that resides within the inverse scattering series that has yet to date not been mined. This shows you the potential for what is possible, not the end result. So here there's a lot of lateral varying. Here there isn't. Here there's a mild amount of lateral varying. So here you're going to see the Feng Lu results very effective, somewhat effective, not very effective, waiting for more terms. Yes? That's an example of the limitation of our current capture. No matter what the capture is, it never requires velocity information. So this is in that cut A. There are three cuts, A, B, C. This is what water speed migration gave, and you can see this move out, indicating that you have in these common image gathers over a different angle, you have some error. When you do HOIS, you don't have that lack of common image gather flatness. A very, very important point is in conventional seismic imaging today, they can't find the velocity directly. That's what happened when they went from time migration to depth migration. They could not find the velocity. So they had to, the common image gather was a way to find some criteria that you would try to look at the output and say, well, that criteria is satisfied, so I probably have the velocity. Looking for a property of the image that would be satisfied. Common image gather flatness is because it's a way to indirectly produce the velocity. It is a necessary but not sufficient condition that you have the velocity, the correct velocity. The correct velocity will have a common image gather flat, but there are other velocities that are not correct that will also. Okay? It's necessary but not sufficient. This is very different. This is not looking for common image gather flat. Common image gather flat here is a byproduct. In other words, this is a direct method that says it doesn't need the velocity. When the common image gather is flat, it means it's satisfied. The direct method has enough capability. So you see here in the C, which is the most laterally rapidly varying place, there's a lot of non-flatness. That's an indication that the direct method is not satisfied. When the direct method is satisfied, you have the depth, period, without any velocity. Understood? Common image gather flatness for a direct method is an indication that the depth is correct. Common image gather flatness as an indirect method, as used in a current seismic exploration, is an indirect indicator that you have the right velocity. And having it satisfied does not mean you have it. And we had many examples at ARCO where it was flat as a pancake and the depth was completely wrong. When drilled there, it wasn't anywhere near. It was one among velocities they found. Okay? So this is a very important. This is a project. It's been a long-term project. It's going to take a lot more time to make this into something that you will have in your toolbox. But when it arrives in your toolbox, it will be in the same place in your toolbox for depth imaging that ISS multiple removal is for multiple removal. When is ISS multiple removal the method of choice? When you have very complicated media that you can't do velocity separation. If I had a multiple in primary that I had a velocity discrimination, I wouldn't use ISS. I'd use radon. It doesn't need a wavelet, it's not so fussy, yes? You just cut. When you have a very complicated media with unknown generators, that's when you call that tool. So at some point in the future, ISS depth imaging will be in your toolbox. There are fundamental issues of gathering more terms that we will progress. There are people who say, and I need to say this right now, that we understand the inverse scattering series internal multiple attenuator, but it's impossible to do the internal multiple eliminator, and absolutely impossible to do depth imaging without the velocity. The truth is, if they say that they understand the attenuator, but you can't do the eliminator, and you definitely can't do the depth imaging, the truth is they don't understand any of it. If you understand that one chart, which had V1, V2, that's the same exact logic, the same cloth that provides that you cut a piece of cloth to produce the ISS internal multiple attenuator, is the same cloth that you're going to build the eliminator and the depth imaging. You either buy it all or you don't. It's one logic. Okay? So you might code it, you might use it, but if you understand where it comes from, these other issues are not issues. It's just a matter of when are you going to provide it, not whether it's possible. The question is, when will this be available? Okay? So I need to make that clear in terms of this frank and forthright conversation. Okay, we're going to go quickly over the direct inversion. Haiyan Zhang applied the direct inversion, which means parameter estimation. Use that V1, V2 to do actual parameter updating. She applied it in a time-lapse sense, using, instead of the difference between properties here and below, the difference between properties here and in the future. So the perturbation operator was a difference in time, the difference in properties over time at the same location. And with the direct inverse from the inverse scattering series, she was able to distinguish a pressure change from a fluid change that was unable to be distinguished from linear methods that were being used at that time. That was an ability to distinguish something which has very similar linear effects. So we'll leave that. We're planning, and you will hear at the next annual meeting, inverse scattering series for velocity analysis. For pre-sol plays, what's the difference between the inverse scattering methods for finding, you know what's above the salt, you want to find the salt velocity. How does the inverse scattering series address that compared to iterative linear? Next, Q compensation without Q. A classic and terribly difficult problem in seismic processing is to compensate for the absorptive dispersive properties of the Earth, because it's extremely sensitive. If you get it wrong, you're going to do harm. You're trying to remove that effect, because this absorption diminishes amplitude. The removal of it grows amplitude and sensitive to noise. Yes? So here's an inverse scattering series method that directly compensates for Q without needing to know anything about Q. This was work by Chris Innanen and Jose Lira when they were here. Now Chris is back in Calgary and Lira's back in Petrogras after his PhD. Here's the example. There's a layer which has Q. There are two primaries. So this primary is subject Q, and the first one is not. That these set of primaries get put into a task-specific inverse scattering series whose function is to compensate the data for Q without knowing it. Okay? That's amazing. And there you go. And this was compared to, in other words, here's the second primary suffering absorption recovered. And this was compared to a model which didn't have Q in the layer. And that second primary matched. That's amazing. Okay? I don't care if you understand the math. It's amazing. Q compensation without knowing or needing Q. Yes? That shows you the potential. So now we're on to another topic. We're going to move quickly through. We, by accident, fell into a method for doing reverse time migration by a method that we feel is the one that you can, one that has the most quantitative and physics-based merit and properties. This has been rolled into a topic of multiple signal or noise. There are two views of multiples. There's the exclusive view that says primaries are signals and multiples are a form of coherent noise. And there's this inclusive view that treats primaries and multiples as some kind of equal opportunity, politically correct method of giving all events equal opportunity. And in that view, primaries and multiples should be migrated. If they're to be used as signal, then you don't need to remove them. So it's very important to understand, and maybe I'll just summarize. Well, first of all, the summary is no one in the real world is migrating a multiple. Okay? What they're doing is they're taking a method. There's three methods of imaging. It looks like we'll be giving this talk. Imaging methods have a wave component, a wave propagation component, and an imaging condition. There are three imaging conditions that Claerbout and his colleagues, others work at the same time, 1970s. One called the exploding reflector model, the second called time and space coincidence of up and down waves, and the third is predicting a source or receiver at a coincident point in depth and asking for t equals 0. These three imaging conditions. Why are we talking about this now? People are talking about migrating multiples. So it's relevant in that discussion to talk about what does migration mean. Yes? If you're talking about migrating something, these are the key imaging conditions, okay, behind migration. The third of these three, we're going to label these Claerbout 1, 2, and 3. Claerbout 3, the prediction of the experiment of a source and receiver at depth, is unmatched in terms of two things, or three things. One is amplitude information at the image, number one. Amplitude as a function of angle. Number two, it gives you specular or non-specular information. If you have a curved or diffractive, it gives you the information to invert a curved or pinch out. That two doesn't. And third, last but not least, it gives you the ability to image direct with a clear theory, not some kind of fix-up, beneath a rapid variation, beneath a rapid discontinuous velocity. So those are three benefits of 3 to 2. When they were first introduced, it was for, these are imaging conditions. They were first introduced for one-way migration. One-way migration means the wave goes down to the reflector, the wave goes up from the reflector. What happened was, there was some point that reverse time migration came into vogue. In other words, in the early times, there was no argument about people who were serious about migration, moving migration to migration inversion. It had to be Claerbout 3. All the work of Stolt and his colleagues, Stolt and Clayton, Stolt and Benson, Stolt and Wegline, all were Claerbout imaging 3. You wouldn't think of anything but that for doing amplitude analysis subsequent to structure. Along came RTM by a group of very innovative, capable people, Dan Whitmore and others at Amico, and in looking at two-way waves, imaging waves that are diving waves, for example, they adopted Claerbout imaging 2, the time and space coincidence of up and down waves. And no harm in that, but that's what it is. And it was able to deal with waves that just don't go down to the reflector. The question of the meaning of the image was raised, and raised by our sponsors to us. And what does it mean, that RTM image? And we started looking at that. But it produced something for diving waves. The question, it became in this idea, there was an up wave that moved down and the down, and you moved down the up wave and down the down wave, and you looked at the time-space coincidence, and that gave you an image. What happened, as often will happen, is that for primaries gives you something reasonable. In fact, in an RTM sense, a locator. It got abused. It became, take something back, take something forward. Whatever you took back and whatever you took forward, the thing that you took back, and you did space-time coincidence of something forward and something else going back, we're going to call the migration of the thing that went back. That's when it got off track. Yes, when they took a multiple and they took it back, and they took a primary and they went forward. Nothing wrong with that. What they're doing in that procedure is they are removing the image due to a primary subevent in the multiple, and obtaining the image due to a subevent primary that they didn't measure, a shorter offset one, when that's the situation, when there is a missing primary. That is not migrating a multiple. That's doing something useful and extracting something useful from a multiple, but to call that a migrating, moving a multiple event from where it occurs in time to where it belongs in depth, that has no meaning. The multiple does not correspond to structure. Okay? So you have to think back to the meaning of migration. So there's nothing wrong with what people are doing in using multiples to enhance imaging. There's no harm. Number one, if you had a full set of primaries, you don't need multiples. Okay. It's an analytic example here that I'm not even going to take you through because of shortness of time. But one of the links that I referred to at the beginning of this talk shows you in detail that as you predict the source and receiver at depth, what happens is every single event that's in the surface data affects the experiment at depth. But as soon as you ask for coincident source receiver at time equals 0, then only primaries in the data affect that image. Multiples, if you left them out or put them in, they may have no difference on the image if you have an accurate discontinuous velocity. And so you, with this new form of RTM that we call Claerbout Imaging 3 RTM versus the current Claerbout Imaging 2 RTM, you can image under a reflector. So the basis of the current, this new Claerbout 3 RTM comes from Green's theorem. Green's theorem says simply, if you know the properties inside a volume, then a surface integral of the field and its normal derivative will predict the field inside, a closed surface, like that. If you have an up wave in this region, and if you take an anti-causal Green's function, you can show the upper surface is all you need, and to predict the field in. The lower surface doesn't count, doesn't contribute. And that is, in addition, you make that Green's function satisfy a Dirichlet condition on the upper surface, and therefore you don't need a normal derivative. From just the field on the upper surface, you predict the field in, which becomes the basis of a migration, a Claerbout 3 migration, because you're predicting what a receiver and then a source will produce. This is getting the receiver down, this is getting the source down. So that is, you can show that this form is exactly Stokes pre-stack migration. Claerbout Imaging 3 for one-way waves. What we set us up to do is do that for two-way waves. So now you're again interested in predicting, but now you have waves moving up and down in the region. If they're moving up and down, anti-causal, causal, none of that's going to get rid of the lower surface for two-way waves. What you have to do is you have to produce a Green's function that, along with its normal derivative, will vanish on the lower surface. A Green's function that, along with its normal derivative, the Green's function and its normal derivative, both vanish on the lower surface. Then you'll get a form like this, which allows you to predict the source and receiver experiment at depth, meaning Claerbout Imaging 3 for two-way waves. This is what we advocate, that you look at if you're serious about amplitude information for RTM, and if you're serious about imaging through a discontinuity. We developed this anyway, but when it came to our multiple signal or noise, we were migrating multiples, we put primaries and multiples in this machinery. Because if you have primaries and multiples in your volume, you have two-way waves. So you need this to migrate primaries and multiples. Yes? So this set of pictures shows what happens for two reflectors when you have, here's just one reflector, you predict the source and receiver above it. That first primary is not this primary. That first primary that you had up shallow is the only event that contributed to the predicted source and receiver. It's the only event that you have, in fact, okay? There. So the primary there contributes to this primary S for small time, and the machine, what machine? The machine we just showed you. This machine predicts the reflection coefficient. Under. Put that source and receiver under. In this region, you have waves going up and down. You need two-way migration, two-way wave migration. When you apply that formula I just flashed on here and predict the source and receiver below, and then ask for time equals 0, you get minus R1. That's a very important message right by itself. When you have now an experiment with a free surface multiple and a primary, and you bring this down, this is showing you figurative, in terms of a figure, what's going on. You can see when this source and receiver are above this reflector, the original primary that was like that is now this. And the original free surface multiple that was this is now this. When you ask for this new experiment, what happens at time equals 0, this contributes and this does not. The original multiple does not contribute to the image. This came from the primary. That's the point. And this continues. On and on. So here's two primaries and an internal multiple, whereas there was a primary 1, primary 2, and internal multiple. Then just watch what happens to those lines as you move the source and receiver down. This primary is what affects this here. There's still a primary that's like that from the second, and the internal multiple is like that. You ask for t equals 0, and only this primary contributes. That internal multiple, the multiples always occur later in the predicted experiment. And when you ask for t equals 0, only primaries contribute. It's that simple. It's not complicated. So I won't go through all this. There's a paper written on this. So if you had, as we do here, an accurate discontinuous velocity, if you have an accurate discontinuous velocity, then you can put primaries and multiples in, or just put primaries in, you're going to get the same image. You will not get the same experiment at depth. But once you ask for t equals 0, the multiples don't contribute. Multiples do not contribute. An accurate discontinuous. You give me a smooth velocity, then primaries can be well located. But with a smooth velocity, every multiple will give you a false event. In practice, we have smooth velocities. In practice, multiples have to be removed. So in the case of accurate discontinuous, multiples don't help. In terms of smooth, they hurt. They never benefit the image. So they're never migrated, in other words. What are people doing who are calling it migration? They're taking a sub-event within a multiple and extracting it as, in other words, the multiple is a combination of events. A combination of events creates the multiple, and through this, take the multiple back and the primary forward. If the primary is measured, they will remove that image due to that primary that's measured and get an image due to an unrecorded primary sub-event. There's a fly in that ointment. The fly is very simple. The method starts off by saying we're going to predict multiples. You can't predict multiples unless you have the sub-events. So if you have missing sub-events because you didn't collect it, you don't know that that's a multiple. If you have this, and you don't know it's a multiple unless you have those two events in your data. So if one guy is missing, so they know that. You go to the different service companies, which I have, our sponsors, and they say, yeah, we understand that. So what we do is we can't predict the multiples. In place of where the multiples belong, we put all the data. And all the data contains the multiples, but it contains primaries too. So the multiples get treated as you want, but the primaries cause artifacts. Because, understood? So that's cause of an artifact. No one knows a way around it. No one knows a way around it is because it's an ad hoc method. It doesn't come from a theory like what Chow Ma and Yang Li are talking about. You got an issue with this term? The theory says there is no issues for the theory. This term has an issue, you look at other terms. If you have an ad hoc sort of seat of your pants method, you don't have a way to fix it. You just have artifacts. Understood? Okay, so is there value in those who are saying we can use multiples to enhance imaging? The answer is yes. If you have missing primaries and you throw in all the data, part of that data will be multiples, and that procedure will give you the effect of imaging missing primary. And if you have missing primaries, that will be better than not having them. There's no primary better than measuring a primary. Okay? But we are advocate having as many ways of providing primaries as possible. Measure them, interpolate them, extrapolate them, use multiples to get an effective primary imaged. All good, but don't call that process migrating a multiple. That event never got migrated. It was undone, taken apart, and a piece of it being used. That event, that piece of it is being migrated, not the multiple. So you say, oh, that's really some kind of academic nitpicking. No, it isn't. Because if you start saying I'm migrating primaries and multiples, people are going to say multiples are a noise. After you finish using your multiple to get some effective primary, you better be removing all multiples before you do depth imaging, because your multiples in your data are going to give you false images. That was the case, that is the case. Okay. You said this already. We're grateful for PGS for showing us, letting us show at the SEG an example where that process had value, where they were able to image a sub-event of a multiple, yes? Not the multiple, a sub-event of the multiple gave added value compared to not using the multiple in that way. Okay, so that is valuable. So now Yang Li Zhou is going to show the difference between Clabout imaging 2 and 3 in terms of amplitude analysis.
Hello everyone, I'm going to give you a comparison of the Clabout imaging condition 2 and 3 for a single reflector. And in this comparison, we test the reverse time migration for Clabout imaging condition 2, and we test the stalled migration for the Clabout imaging condition 3. Here's the model I used. It's a one reflector model. And here shows the reverse time migration image for one shot gather. And here is a blow up of the image. And we can see there is a blur here. And there are two reasons for this blur. The first reason is that the wavelet. The wavelet will contribute to this blur. And the second reason is the line source, because in this data was generated by a line source. So the wave field generated by line source will have a tail, and that tail will also contribute to the blur. And people usually add all sources together and assumes the blur and the artifacts will go away. However, adding all the sources together in RTM doesn't have a physics meaning, and it will also lost the amplitude information. And here is the stalled migration image, and we can see, here is a blow up of the stalled migration image. We can see the image is very flat, and we can also get the angle-dependent reflection coefficient from the unclasped stalled migration. Thank you.
Very good. So a very important point is that Yang Li used the same exact data for Clabout imaging 2 and 3. And so all these tails and wavelet issues, yes, were in both. It wasn't a different data, which would be an unfair comparison. So it's important to understand that we are going to pursue this Claerbout Imaging 3. We meaning Chung Fu working with Professor Fang Lu, looking at what are the benefits in comparing 2 and 3, looking at issues of implementing for lateral and vertical varying media, and how they differ in predicting a wave below a rapid variation. Yes? So we have pretty well covered everything on this chart. Again, the summary is every single item on this chart is we take ownership for. We don't start and say, well, we want to do depth imaging and all this other is, I don't know, it's somebody's business. Everything's our business. From the minute that the data is recorded, every single separation, we look to add value. And we have added value that we made clear in these presentations. We plan to continue. The big thing, if you want to know, if you have to say, what are you going to be getting in terms of code that makes a difference to your company in the next year, is you're going to get a 1D internal multiple eliminator. And you're going to get a Claerbout 3 RTM code in X and Z. Those are big, game-changing capabilities. The plan to produce multi-dimensional, meaning from a multi-dimensional unknown Earth, internal multiple elimination is what's coming down the road. That's the next big delivery. It has to come from the inverse scattering series if it doesn't require subsurface information. And there's no other candidate place to produce that, to deliver that. And if you have interfering primaries and internal multiples, offshore and onshore, if that matters, and that happens a lot, then that's reason enough to be interested in projects like internal multiple and all of the prerequisites that are needed for that to be successful. This by itself is not going to succeed. This is a coupled link chain. The people in this group are coupled to each other in terms of we need each other, in terms of deliverables. And so one of the things we're going to do is we're going to take an elastic one-dimensional data set and take it through, in a marine sense, through the entire chain. Every separation, reference wave, scattered wave, deghosting, free surface multiple, internal multiple, attenuation, internal multiple, elimination, and then beyond. Okay? So then you see, well, what if you didn't do that pre-processing step that well? Yes? What's going to happen? You have a control on the whole chain. For offshore, we're pushing the offshore elimination activity, also ocean bottom for 4D. For onshore, we need that pre-processing progressed. And we're going to look at the ISS direct nonlinear parameter estimation as a velocity estimation. This group is not some kind of religion against velocity. Okay? We're open. We think we've never looked at ISS direct parameter estimation as a velocity analysis tool. We're going to look at that. We're going to have a first report on that in June at the annual meeting. Okay? This is a diagram that's for buried sources and receivers. For buried sources and receivers, often the objective is to do 4D. 4D where there's some location here where you're looking for time differences. What often happens is in the near surface, you have temporal differences in the near surface. The measurements here for separating reference wave from scattered wave, doing deghosting. We're developing methods to do two things. One is to do all the processing in this acquisition without needing to know anything below, above, or at the measurement surface, at depth. And in addition, to be able to isolate the part of the change in the scattered wave over time that's due to the change below and not due to the change in the weathering layer. You'll see early theory on that at the annual meeting. That's what this slide is describing. So this is what I mentioned in terms of cold delivery. Again, this is the chart. This is the onshore chart. And Jing-Wu is taking us to the first early steps. Once we get those early steps, all the machinery for the marine can start to act. But we have to deal with that near surface, all that wave separation first. This is the group. I'm indebted to the group. This is our sponsors, extremely indebted. And I'll just end by saying, we know that the methods we pursue are not conventional. They're not considered normal. They're not mainstream. And we know there's a large amount of skepticism in general for methods we pursue. The only words I can say is that multiplies the degree of gratitude and appreciation I have for sponsors supporting us in the face of that skepticism. And I could just say, please remember that the things that we have delivered in the past that you are now using at CGG, PGS, Schlumberger, and within your own sponsor companies were considered completely lacking in credibility when they were first proposed. And now they're conventional. So I appreciate the opportunity, we appreciate the opportunity to give us a chance to do that again. Okay, thank you.